press the bell icon on the YouTube app and never miss another update.
In the previous class, we discussed about photoelectric effect and also the dual nature of matter, that is matter waves, and we have also derived expression for de Broglie wavelength, and we have expressed de Broglie wavelength in terms of momentum, in terms of the kinetic energy of the particles, and in terms of that accelerating potential. And here we have the de Broglie wavelength of electron, right, accelerated through a potential difference V is shown to be 12.27 angstrom unit divided by square root of V, right. So this is the right theoretical value of de Broglie wavelength, right, of electron when accelerated through a potential difference V, right. Now with that, now it is clear that according to de Broglie, material particles in motion exhibit right wave nature, but since we have lambda is equal to h by mv, right. Now this h is of the order of minus 34. Therefore, in case of macroscopic particles, right, the velocity is very small, of the order of 10 raised to the power of 2, right. Masses are of the order of 10 power 2, 10 power 3 kg. Therefore, for macroscopic particles like a cricket ball, right, a football, right, a plane, a rocket, a bus or car, right, the wavelength is of the order of 10 raised to the power of minus 30 meter. It is a very small, right, wavelength. Therefore, we can hardly observe, right, wave nature of right macroscopic particles. But however, in case of microscopic particles, their mass is very small. If we take electron, it is of the order of minus 30, right, kg. And other, right, atomic and subatomic particle 10 power minus 27 kg. At the same time, these microscopic particles are moving with very high speed of the order of 10 raised to the power of 6 meter per second. Therefore, for microscopic particles, right, this comes out to be of the order of 10 power minus 10 meter to 10 power minus 12 meter, right. Now that is considerably large compared to the microscopic. Therefore, right, we can observe the wave nature of a particle only in the case of microscopic particles like electron, proton, neutron, nucleus, etc. Right. So therefore, this electron, right, in motion, right, exhibits a wave nature, that is, it is associated with matter waves. Now, Davison and Germer experimentally demonstrated wave nature of light, right, the wave nature of electron, right. For that, we need to understand, right, the diffraction of light. Now, diffraction of light means the bending of light around the corner of an obstacle and entering into the geometrical region. Suppose if we have a very narrow slit of width d, suppose we have a screen placed in front of the slit. So when a beam of light, monochromatic beam of light of wavelength lambda, right, it incident on, right, this narrow slit Now it bends around the corners of the slit, right, and enters into the region of geometrical shadow. This phenomenon is called as diffraction of light. As a result of diffraction of light, on the screen exactly in front of the slit, right, we will observe, right, a fringe pattern, right, consisting of alternate bright and dark bands, right. Suppose if the slit is a rectangular slit, we observe alternate bright and dark rectangular bands on that screen, right. Now that pattern consists of the central band formed exactly, right, in front of the slit, right, and that has the maximum width and the maximum brightness among the other fringes, and it is called as central maximum, right, and it is followed by, right, the diffraction, right, maxima and minima, that is alternate bright and dark band. Central one is called as, right, principal maximum, which is having the highest intensity among the bands, followed by alternate bright and dark bands of varying intensity and varying width. That is called as diffraction of light, right. Not only the light wave, all types of waves, right, electromagnetic or, right, longitudinal waves, they exhibit diffraction, right. So interference, diffraction and polarization are the properties of a wave, right. However, right, polarization is exhibited only by electromagnetic waves. Longitudinal waves do not exhibit the phenomenon of polarization, right. Now here, when light passes through a narrow slit, it produces a diffraction pattern consisting of alternate bright and dark bands, right. It is because of wave nature of light. According to Bragg, right, the first order diffraction maximum, that is for n is equal to 1, lambda is equal to 2d sin theta, where theta is the angle of diffraction and d is the width of the slit width, right. This is according to Bragg's equation, right. When the first maximum, right, the first bright band, that lambda is equal to 2d sin theta. This equation is called Bragg's equation, right. So suppose instead of light, if we use electron, right, accelerated through a certain potential difference, because electron is a charged particle, we can move a charged particle only in an electric field, that is by applying a potential difference, right. Now when an electron, suppose, is made to incident on this, not this slit, suppose we say that, let us imagine that if electron is incident on this slit and it produces a diffraction pattern, right, that means at different parts of the screen, right, intensities of electrons are different, at certain point maximum, at certain point minimum, then we can say that the electron exhibits diffraction. If electron being a particle exhibits diffraction, means it is associated with wave nature, right. So the Davison and Germer experiment, right, established that, right, electrons exhibit diffraction, that is the very basic property of a wave, right, and we can measure the experimental value of, right, the de Broglie wavelength, right, using that experiment, right, and using that Bragg's equation, and we will compare that value with the theoretical value of de Broglie wavelength of electron, that is lambda is equal to 12.27 angstrom minute by square root of V. If those two values comes out to be, right, nearly equal, then it is clear that like other waves, right, electrons exhibit diffraction, that means electron motion is associated with the wave nature, right? Now let us take up that experiment. Davison and German experiment to demonstrate wave nature of electron by experimentally showing that, right, electron exhibits a diffraction. Right? Now that experimental arrangement, it consists of a filament, obviously a tungsten filament, right, and it acts as a cathode by emitting electrons, right. Now this filament is connected to a battery. This filament is connected to a battery, right, so that a current flowing through the filament, right, heats up the filament, right. When a filament is heated to a suitable temperature, it emits electron, right. Now we need to apply a potential difference, right. For that we consider an anode A with a fine hole here to make electrons to emit as a parallel beam, right. Now a potential difference is applied between cathode and anode by using a variable battery, right. This is battery whose potential difference V, right, can be varied. Negative terminal is connected to cathode and positive terminal is connected to anode, so that there is a potential difference between cathode and anode, right, and the electrons, right, they emitted from the cathode, they are attracted towards the anode and a fine beam of electrons, right, is emitted out of this hole, right. And theoretical value of this wavelength can be calculated. Lambda is equal to 12.27 angstrom unit by square root of V. Now here we have a nickel crystal. We place a nickel crystal in the path of light, electron. A fine beam of electron, right, it incident at a point O, right, on the crystal. This is the point of incident, and this is right, incident electron beam. Now this incident electron scattered in all directions, right, with the angle of scattering. Right. Now suppose if we say a beam of electron scattered through an angle phi, this is a scattered electron beam. Now the intensity of scattered electron beam, that is the number of electrons scattered per second, right, can be measured with the help of a detector. Here we have a detector D, right, that measures the intensity of scattered light. Now the detector is can be arranged to rotate about the point of incidence, so that we can measure the intensity of scattered electron at different angle of incidence. That means in this experiment, electron is accelerated through a potential difference V, made to incident on nickel crystal at a point, and we measured the intensity of scattered light, I mean electron, right, for different angle of scattering. Here, angle between the direction of incident electron beam and the direction of scattered electron beam is this angle of scattering. Now, if we take a straight line here, right, then this angle is theta and this angle is also theta, right. So, theta plus phi plus theta is equal to 180 degree. Now, this experiment is repeated for different, right, values of potential difference, starting from a small value. So, 40 volt, 41, 42, 43, up to we can take the 60 volt we can able to measure. In the range from 40 to 60 volt, we can measure, right, the intensities of, right, scattered light, right, with angle of scattering for different values of accelerating potential, right. So, when we plot a graph of intensity of scattered light, right, against, right, the angle of scattering, right, for different, right, potentials, we will obtain a set of graph here. Now, here this is intensity of scattered light. Say at angle V is equal to 44 volt, right. Now, when we observe the graph, the intensity of scattered electron, that depends upon angle of scattering, right. Intensity of scattered electron varies with the angle of scattering, and here we observe a kink, right, or a bump, right, at an angle of, right, scattering is equal to 50 degree, right. As we go on increasing the accelerating potential difference or voltage, the size of bump goes on increases. The size of bump goes on increases. Now, the size of the bump, right, again this is also at an angle 50 degree, right, the size increases, and at, right, in accelerating voltage of 54 volt, the size of the bump becomes maximum. That means at this voltage, the angle of scattering at 50 degree, the intensity of electron is maximum. On further increasing the voltage beyond 54 volt, now the size of the bump gradually decreases. That means the size of the bump at 50-degree angle of scattering is maximum at 54 volt, right? And below 54 volt and above 54 volt, right, it becomes right smaller one, right? That means we can come to the conclusion that, right, intensity of scattered light is maximum at 54 volt, right, at angle of phi is equal to 50 degree, right? Now this maximum intensity at 54 volt is due to the diffraction of light, particularly selectively at 54 volt and 50 degree angle of scattering, the intensity of electron becomes maximum. Even in diffraction experiment also, right, at a different angle of diffraction, the intensities will be different, right? Now this maximum intensity may be due to diffraction of electron, right, within the atomic planes of the nickel crystal, right? Now from Bragg's equation, so for first order maximum, that is for n is equal to 1, right? Now that lambda is equal to 2d sine theta, equation 1. Here the value of d is equal to 0.61 angstrom unit. That is the spacing between the atomic planes of nickel crystal, which acts as a slit here, right? Now here to calculate theta, now this from previous figure, I have already told theta plus phi plus theta is equal to 180 degree, or theta is equal to 180, this is minus phi is equal to 50 degree there by 2, that is equal to 65 degree. Therefore, right, now the lambda is equal to 2 into 0.61 angstrom unit into sine 65. This lambda comes out to be 1.66 angstrom unit, equation 2, right? So the experimentally calculated value, this is experimental value of, right, the wavelength of electron which undergoes diffraction is lambda is equal to 1.66 angstrom unit. And we know the fact that the diffraction effect, right, is maximum when wavelength of light or any wave is comparable with the width of the slit or size of the obstacle. Then only we can able to observe the maximum diffraction effect, right? Now here we can calculate the theoretical value of de Broglie wavelength. That is lambda is equal to 12.27 angstrom unit by square root of V. That is equal to 12.27 angstrom unit divided by, right, square root of, right? So we got the maximum size of the bump and maximum intensity at 54 volt, right? That is at 54, or lambda comes out to be 1.65 angstrom unit, right? This is theoretical value of wavelength of electron. This theoretical value and experimental value are in well agreement with each other, right? You got my point? Now therefore we can come to the conclusion that the electron exhibits diffraction. When electron exhibits diffraction, no doubt that the motion of electron is associated with the wave nature, right? Therefore, this electron in motion exhibits wave nature. So, this is how Davison and Germer experimentally demonstrated the wave nature of electron in motion. That is, it exhibits a diffraction, right, pattern, right. Now, in fact, here for 54 volt, right, at that particular volt, the wavelength of electron, right, matches with the spacings, and we will get, right, the maximum, right, intensity. For lambda less than that or more than that, right, now the intensity is not maximum, that is minimum, right. Therefore, this experiment clearly demonstrates the wave nature of, right, and that completes your real nature of matter. Here the important thing is electron emission, right. Usually there will be 1 mark or 2 mark question on electron emission and types of electron emission, right. And important thing is, right, as far as board examination is concerned, the laws of photoelectric effect, right, and Einstein's explanation for photoelectric effect are asked for so 5 mark, right. And sometimes the photoelectric equation, the derivation h nu is equal to h nu naught plus half mv square, right, is asked for, right, 3 mark question, and there may be a problem, right, 5 mark problem, right, in photoelectric effect part, not in dual nature of de Broglie wavelength part. In that part we are having a problem. Now we take so list of formulae here. Now, number 1 we have, right, energy of photon, right, E is equal to h nu or is equal to hc by lambda in joule. Here generally the energies are expressed in terms of electron volt. Now in this case E is equal to h nu by E, right, to convert joule into electron volt, is equal to hc by, right, lambda into E in electron volt, right. Straight away if we need energy in joule, that is equal to h nu or it is equal to hc by lambda, or we need to calculate energy in electron volt just divided by E, that is 1.6 into 10 power minus 19, right. Now second one we are having power of bulb, right. So P is equal to N h nu by Ta, where N by T represents number of photons emitted per second, h is Planck's constant, nu is frequency of radiation, A is area of cross section, or that is equal to nhc by, right, Ta lambda in terms of wavelength. And third one we have Einstein's photoelectric equation, E. So E is equal to 5 plus maximum kinetic energy, it is the original form of equation. B, h nu is equal to h nu naught plus half m v maximum square, where m is mass of electron, h is Planck's constant. C, Hc by lambda is equal to Hc by lambda naught plus, right, half m v maximum square. Here the terms which we are using is incident frequency, incident wavelength, threshold frequency, threshold wavelength, Planck's constant, speed of light in vacuum, that is 3 into 10 raised to the power of 8, mass of electron and velocity of electron. These are all the terms which we are going to use in this equation. Now the fourth one. Now we have the stopping potential EV, right? It is equal to kinetic energy equal to half mv square. So this Vs, the stopping potential Vs is equal to, it is kinetic energy in EV divided by E. So stopping potential, right, is equal to kinetic energy expressed in EV divided by EV, right. So this when we divide it by 1.6 into 10 power 19, right, now that EV get cancelled here, then we will get the value of potential in volt, right. Right. So these are all the formulae which we are going to use in solving numerical problems, right. So here, for the convenience sake, I will write the problem on the board and then we solve it, right. I will write the problem on the board, then I will read it. Right. Now problem number 1. What is the energy of a photon of frequency 1.6 into 10 raised to the power of 18 hertz in joule and in electron volt. So we have given, right. So frequency of incident radiation nu is equal to 1.6 into 10 raised to the power of 18 hertz, right. What we need to find? We need to find energy E is equal to what? Both in joule and in electron volt. Now we have energy E is equal to h nu, that is equal to, right, 1.6 into 10 raised to the power of 18 into h value. Usually the value will be given 6.625 into 10 raised to the power of minus 34 into 1.6 into 10 raised to the power of 18. That E comes out to be equal to, right, 1.06, right, into 10 raised to the power of 15 joule. 1.06 into 10 power minus 15 joule. How to convert this into electron volt? Right, this E is equal to, right, 1.06 into 10 power minus 15, right, that divided by 1.6 into 10 power minus 19 to convert it, and that comes out to be equal to 6.625 into 10 raised to the power of 4 right, electron volt. The value comes out to be 6.625 into 10 raised to the power of 4 volt. Just directly to calculate this one, just we will take E is equal to h nu by E, then we will obtain this value. Now, problem number 2. A source of 60 watt is emitting light of 700 nanometer. Calculate the number of photons, right, emitted per second. Right. Now we have given, right, power of bulb, right, P is equal to 60 watt. We need to calculate that number of photons emitted per, number of photons, right, emitted per second. N is equal to what? That is when T is equal to 1 second. Now we have the formula, power P is equal to, right, N H nu by T. Power P is equal to N H nu by T, where we calculate N H nu by T. So in the previous one, that power, I have written power P is equal to NH nu by TA, but actually that is intensity, right? You make a correction, it is not EA, right? P is equal to NH nu by T, but intensity I is equal to NH nu by TA, right? You make a correction there, right? Now this N is equal to Pt by h nu, that is equal to power 60 into 1 second divided by 6.625 into 10 raised to the power of minus 34 into, right, nu, that is wavelength is given, so that we will take it as in terms of wavelength, that is equal to NHC by T lambda. Therefore it becomes N is equal to Pt lambda by Hc, that is power P 60 into 1 into this is 700 nanometer, that is 700 into 10 power minus 9 divided by 6.625 into 10 power minus 34 into 3 into 10 raised to the power of 8. Right. Now that comes out to be 7 into N is equal to 7 into 10 raised to the power of 8, right, photons per second. The number of photons emitted per second is 7.8. You will take the just photon, right? So number of photons are 7 into 10 raised to the power of 8 photons per second. Right. Now, third question. A photon of frequency 5 into 10 raised to the power of 14 hertz. 5 into 10 power 14 hertz is incident on a metal surface. Incident on a metal surface if the threshold frequency of the metal is 3 into 10 raised to the power of 14 hertz, right? Calculate number 1, the energy of photon in EV. In EV. Number 2, right, the photoelectric work function in EV. Third one, maximum kinetic energy of electrons in EV. Fourth one, stopping potential, and fifth one, maximum velocity of emitted electron, right. So now a photon of frequency 10 power 14 hertz is incident on a metal surface if the threshold frequency of the metal is 3 into 10 raised to the power of 14 hertz. Then we have to calculate number 1, the energy of photon in EV. Number 2, photoelectric work function in EV. Number 3, maximum kinetic energy of electron in EV, stopping potential, and maximum voltage, right. So we have given, right, I will take it here, right. Now we have given values. So incident frequency nu is equal to 5 into 10 raised to the power of 14 hertz and nu naught equal to 3 into 10 raised to the power of 14 hertz. We need to calculate number 1, incident energy is equal to what in EV. Number 2, photoelectric work function phi is equal to what in EV. Number 3, maximum kinetic energy is equal to what in EV. Fourth one, stopping potential Vs. What is fourth one? Maximum kinetic energy. Fourth one, yes, stopping potential Vs is equal to what? And fifth one, right, maximum velocity of emitted electron is equal to what? Right. Now, so for first one, we have this formula E is equal to h nu, that by E in electron volt. This is 6.625 into 6 into 10 raised to the power of into 10 power minus 34, that into this is 5 I think, yes, 5 into 10 raised to the power of 14 divided by 1.6 into 10 power minus 19. Now that comes out to be equal to 2.07 eV. 2.07 eV. Now the second one, photoelectric work function. Now phi is equal to, right, this is h nu naught by E, right, that is equal to 6.625 into 10 power minus 34 into 3 into 10 raised to the power of 14 divided by 1.6 into 10 power minus 19, that comes out to be equal to 1.24 eV. 1.24 eV. Now the third one, right, we have energy E is equal to 5 plus kinetic energy maximum. So kinetic energy maximum is equal to E minus 5, that is equal to 2.07 minus 1.24, that is equal to 0.828 electron volt. So B is equal to 0.828 electron volt. Now we need to find the maximum, stopping potential. That's, we have the stopping potential E into Vs is equal to kinetic energy maximum. So that Vs is equal to, right, kinetic energy, that is Vs, the kinetic energy maximum by E, that is equal to kinetic energy maximum 0.828 into, now stopping potential comes in volt, that is SI system. Now let us convert it into joule. That 1 eV is equal to 1.6 into 10 power minus 19 divided by E 1.6 into 10 power minus 19, that is equal to 0.828 volt. So the stopping potential comes out to be 0.828 volt. Now we need to find the maximum velocity. See here, the kinetic energy is 0.828 eV. Now we have kinetic energy maximum comes out to be 0.828 eV, that is equal to 0.828 into 1.6 into 10 power minus 19 joule. It is because electron volt is a convenient unit, but joule is the SI unit. When we calculate the maximum velocity, its unit comes out to be in SI system, meter per second. Therefore, we have to convert it into joule, right? So while calculating velocity, right, using the kinetic energy, if the kinetic energy is in electron volt, then you have to convert it into joule. Now we have half m V maximum square is equal to kinetic energy maximum. So V maximum is equal to 2 kinetic energy maximum divided by m, the square. So V is equal to square root of 2 kinetic energy maximum divided by m. So V is equal to square root of 2 into, right, 0.828 into 1.6 into 10 power minus 19 divided by mass of electron 9.1 into 10 power minus 31. You calculate that, V comes out to be, right, 5.4 into 10 raised to the power of 5 meter per second. Right. Now, another problem number 4. The work function of cesium metal is 2.14 eV. When light of frequency 6 into 10 raised to the power of 14 hertz is incident on the metal surface, photoelectric emission occurs. Find A, energy of incident photon, and B, maximum kinetic energy of photoelectron. Right. So we have given the problem is the work function of a cesium metal is 2.14 eV. When light of frequency 6 into 10 raised to the power of 14 hertz is incident on the metal surface, photoelectric emission occurs. Find energy of incident photon and maximum kinetic energy of photoelectrons. Now we have given, right, photoelectric work function phi is equal to 2.14 eV. Right. Now the frequency of incident radiation, right, nu is equal to 6 into 10 raised to the power of 14 hertz. Now we need to calculate A. So energy of photon E is equal to what? B, right, kinetic energy maximum is equal to what? Right. Now we have E is equal to h nu. Since phi is given in terms of electron volt, so again finding this in terms of electron volt, E is equal to h nu by V, right, h 6.625 into 10 power 14 into, right, nu 10 power minus 34 into 6 into 10 raised to the power of 14 divided by 1.6 into 10 power minus 19. Now that comes out to be equal to 2.486 eV. Now B, we have E is equal to 5 plus kinetic energy maximum. Therefore kinetic energy maximum is equal to E minus 5. E minus 5, that is E 2.486 volt minus this is 2.14, or kinetic energy maximum is comes out to be 0.3 0.346 eV. So here work function is given in electron volt. Therefore, we have calculated energy, incident energy in electron volt, and finally we got the right kinetic energy also in terms of electron volt. Now, problem number 6. So, ultraviolet radiations of wavelengths 800 angstrom unit and 700 angstrom unit when allowed to fall on a photosensitive surface are found to liberate electrons with maximum kinetic energies of 2 eV and 4.22 eV respectively. So find Planck's constant. Find the value of Planck's constant. Now we see here ultraviolet radiations of wavelength 800 angstrom unit and 700 angstrom unit, right, incident on a photosensitive surface. They found to emit photoelectrons of kinetic energies 2 electron volt and 4.22 electron volt respectively. Find the value of Planck's constant. Now we have given, right, lambda 1 is equal to 800 angstrom unit, that is 8 into 10 power minus 8 meter. Now the kinetic energy maximum, what is 1, emitted due to this radiation is, right, 2 eV. Now since here kinetic energy is given in terms of electron volt, but we need to calculate the Planck's constant, right? Therefore, we need to convert this electron volt into joule, that is 2 into 1.6 into 10 power minus 19 eV, right? That is equal to, right, 3.2 into 10 power minus 19 eV. Now lambda 2 is equal to 700 angstrom unit, that is equal to 7 into 10 power minus 8 meter. Now kinetic energy 2 is equal to 2 in, it is 4.22 eV, that 4.22 into 1.6 into 10 power minus 19, that is equal to, this value is 6.752, right, into 10 power minus 19, right, it's not eV, this is joule, again joule. Now what we need to calculate? We need to calculate H is equal to what? So here we have given incident wavelengths and corresponding the kinetic energy, right? Now both cases photoelectrons are emitted by the same photoemissive surface. Therefore, photoelectric work function phi remains constant. Now, using this equation, Hc by lambda 1 is equal to Hc by lambda is equal to, right, Hc, or we can write phi plus kinetic energy maximum, that is incident energy Hc by lambda is equal to phi, right, work function plus kinetic energy. Now, in first case, we have Hc by lambda 1 is equal to phi plus, right, 3.2 into 10 power minus 19. In second case, Hc by lambda 2 is equal to phi plus 6.752 into 10 power minus 19. Now, let us take it as equation 1, this as equation 2. Now, subtracting equation 2 minus equation 1, that implies, that is Hc by lambda 2 minus Hc by lambda 1. Now, this get phi get cancelled. If we subtract that value, that comes out to be 3.55, that is plus 3.55 into 10 raised to the power of minus 19. Now here, no, this is equals, not plus. That comes out to be phi get cancelled, that is equals. Now Hc into 1 by lambda minus 1 by lambda 1 is equal to 3.55 into 10 power minus 19. Now, so here Hc into, this can be written as lambda 1 minus lambda 2 divided by lambda 1 lambda 2, that is equal to 3.55 into 10 power minus 19. Therefore, H is equal to, right, lambda 1 lambda 2 into 3.55 into 10 power minus 19 divided by this C into, right, this is lambda 1 minus lambda 2, or H is equal to, this is lambda 1 8 into 10 power minus 8, 7 into 10 power minus 8 into, this is 3.55 into 10 power minus 19 divided by, this is 3 into 10 power 8, this is 8 into 10 power minus 8 minus 7 into 10 power minus 8. You calculate that, X comes out to be 6.63 into 10 power minus 34 joule. Right. So, the problems will be very simple in this case, because the main formula is incident energy is equal to work function plus maximum kinetic energy of electron, right? Okay, we shall continue in the next class.